Homeostatic control of blood pressure. Did you know that you need lower blood pressure when you're horizontal than when you're vertical? What happens when you get up? How does the body maintain constant blood pressure as we change positions? Rapid changes in position require a rapid response. Through homeostasis, our autonomic nervous system adjusts heart rate and arterial diameter to keep blood pressure in an acceptable range regardless of body position. For example, if you lie down, blood pressure that was fine when you were standing will be too high in the new position. If you rise, the lower blood pressure that was adequate in the sleeping position would be too low to get blood to the brain, and you might pass out. Here's how the nervous system helps control blood pressure. Pressure is constantly being monitored by stretch receptors at the aorta, the vena cava, and the carotid artery. When arterial pressure increases, stretch receptors in these locations are stimulated, and a message is sent to the heart rate center on a part of the brain called the medulla oblongata, which is part of the autonomic nervous system. We're not conscious of what's going on there. Here, sympathetic nerves and parasympathetic nerves are going to kick into action. Fewer impulses are going to travel along the sympathetic nerve and more along the parasympathetic nerves. And the sympathetic and parasympathetic nerves that are hooked up to the pacemaker in the heart will basically send a message to reduce cardiac output, that is, slow the heart rate down. As a result of reduced cardiac output, pressure in the arterioles will be reduced and the problem will be corrected. This is why it's a negative feedback mechanism. But if we go back to the heart rate center, it also has sympathetic and parasympathetic nerves hooked up to arterioles all over the body. And if you recall from our discussion on blood vessels, you'll know that arterioles have muscles surrounding them which allow them to constrict or dilate. Well, if the pressure is getting high, the arterial diameter will actually increase. They'll dilate as a result of more parasympathetic stimulation. With wider diameters, they can accommodate greater pressure. It's like making your garden hose twice as wide while you still have the same amount of water flowing through it. The end result of that is that the pressure in the arterioles will be reduced, and so it corrects the situation, and it's a negative feedback situation. And what about the other scenario where the blood pressure drops because you've just stood up really quickly from lying down? You need to correct that really quickly before you pass out because you have to ensure that you're getting adequate blood and therefore adequate oxygen to the brain. So the stretch receptors in the aorta, the vena cava, and the carotid artery will be stimulated less. This triggers a message to the heart rate center, and sympathetic impulses increase, parasympathetic impulses decrease. The result in the pacemaker is that the messages speed up and the cardiac output increases as the heart begins to beat faster, and this results in an increase in arterial pressure, which will improve the situation of too low blood pressure. Now, the heart rate center is also sending a message to arterioles all over the body to reduce their diameter, so those muscles will constrict and cause a narrower lumen of the blood vessel, and pressure will go up. So this happens very rapidly. If you're lying down, you wake up and you very quickly stand up. If you could monitor your heart rate in that moment, you would actually notice an increase in your heart rate. So this homeostatic mechanism controls blood pressure when very rapid changes of position are occurring, and it adjusts our blood pressure for whatever position our body happens to be in. Blood pressure can also be controlled by controlling water in the body. 75% of the body's weight is due to water. We routinely lose water when we breathe, sweat, urinate, or have a bowel movement. This loss in fluid can affect our blood volume if the fluid is not replaced. Hormones control water loss by controlling how much water is lost to the kidneys. The filtration unit of the kidneys is the nephron. At each nephron, fluids are pushed out of the blood due to blood pressure. Wastes remain in the nephron tubules and are excreted as part of the urine. But materials that the body needs to keep, including water, need to be reabsorbed into the blood. How much water gets reabsorbed depends on how hydrated the body is, because that affects blood volume. Hormones are secreted in response to drops in blood pressure due to drops in blood volume. The effect is a rise in blood pressure. Here's how it works. If blood volume in the arterioles drops because we're sort of dehydrated, blood pressure will also drop. This is noted at the kidneys, where a hormone called renin is secreted or put into the blood. It travels through the circulatory system, but as soon as it hits the blood, some chemistry happens in the plasma. Another hormone called angiotensin II forms, and angiotensin II has a few effects. It has an effect on the arterioles, and it'll actually cause their diameter to be reduced. By reducing the diameter, the pressure should be improved somewhat. The angiotensin II also circulates through other parts of the body, and when it reaches the adrenal cortex, the outer part of the adrenal gland which sits atop the kidneys, it causes another hormone to be secreted, aldosterone. And aldosterone circulates through the bloodstream, and when it reaches the kidney tubules, it actually triggers reabsorption of sodium into the bloodstream. And because of osmosis, water follows the sodium into the bloodstream. This reduces the amount of water that is excreted at the kidneys, and as a result it slows the decrease in volume due to dehydration. Now in a situation like this is a temporary measure, and you would probably be feeling thirsty by the time this mechanism was kicking in. So the only remedy, you can slow down the rate at which you lose water, but you eventually are going to need to replace that water because, of course, all our cells are bathed in it and all of our chemistry happens in it. So this is a measure by the hormones to slow down the rate of dehydration. Let's say you are really well hydrated. As a matter of fact, you've been drinking a lot of water and your blood volume is up. This would cause a rise in blood pressure as well, and at the kidneys, less renin would be secreted. As a result of that, less angiotensin II would be formed in the plasma, and the arterioles would respond by increasing their diameter, and that would accommodate the increased pressure and alleviate some of the pressure, so it would correct the situation. Okay, because of reduced angiotensin II, the adrenal cortex will be secreting less aldosterone, and that in turn will cause less sodium and water reabsorption at the kidneys, which means more of it stays in the tubules and becomes a part of the urine. So excretion of water increases. This is going to reduce the amount of volume in our blood, and so it corrects the situation. And so you've probably been in this situation where you've maybe overcompensated, or you just drank too much water or liquid, and as a result of that you need to go to the bathroom, and it's because this mechanism is kicking in. Okay, so we've examined two mechanisms that control blood pressure, one that does it by controlling cardiac output and diameter of blood vessels through the action of nerves, and a second that controls the blood volume by controlling how much water actually is allowed to leave via the kidneys.